Oftentimes for genes with two alleles, the convention is to give them standard letters. So the frequency of our A1 allele we oftentimes refer to as P. And the frequency of our A2 allele we oftentimes refer to as Q. So the frequency of one plus the frequency of the other, in this case in a two allele gene, should always add up to 1. That's a key point. So some genes have multiple alleles, perhaps more than 2. If that's the case, we calculate frequencies basically in the same manner, but remember that each frequency, each allele frequency must add up to 1. So in the case of a 3 allele gene, we might have P plus Q plus R must equal 1. Make sense? Okay, so to recap, we've got chromosomes, we have genes occurring at specific locations on chromosomes. Diploid organisms have 2 chromosomes, 2 copies of each chromosome. And we have these alleles for each gene, and alleles are these forms of a gene. So if we know something about the alleles, we know something about how many individuals and populations carry these alleles, we can estimate, again, allele frequencies and genotype frequencies. And this is where the Hardy-Weinberg principle comes into play. The principle was named after Gottfried Hardy, who was an English mathematician, and Wilhelm Weinberg, who was a German physician. And they developed this principle in the early 1900s. And what it states is that if a population is large, its individuals are mating at random, and there's no mutation or migration or any form of natural selection occurring, then the genotype frequencies should remain constant from one generation to the next. And not only that, those genotype frequencies can be predicted by the following equation. The equation is p squared plus 2pq plus q squared equals 1. So the p squared term in this equation represents the genotype frequency for A1, A1. The 2pq term here represents the genotype frequency for A1, A2. And our q squared term here represents the frequency of genotype A2, A2. So remember that the sum of our genotype frequencies, 1, 2, and 3 here, should always add up to 1. For example, if we jump back to our red fox population, if the frequency of our A1 allele, P here, is 0.75, and the frequency of our other allele, A2, which we'd represent by Q, is 0.25, then the Hardy-Weinberg principle would suggest that at equilibrium, here that meaning that the population is large, there is random mating occurring and no mutation migration or natural selection, then the genotype frequencies should be the following. The frequency of our A1, A1 genotype then would be p squared. So from our equation, the p squared term represents the frequency of A1, A1. So that's simply p times p. So we know in this population our p is 0.75. So we multiply 0.75 times 0.75, and that then gives us a value of 0.5625. What does that mean? It means under Hardy-Weinberg, at equilibrium, we would expect the frequency of the A1, A1 genotype to be 0.5625. In other words, 56% of the individuals in that population should be A1, A1. So let's look at the next genotype here. What is the frequency then of our A1, A2 genotype? So remember from the equation, that's represented by the term 2pq. So that's 2 times p times q. So that's 2 times what we know to be p, and that's 0.75. That's p. times 0.25, which we know is Q. So that then gives us a value of 0.375. So again, under Hardy-Weinberg, we expect that 37% of the population to be A1, A2, or the frequency of the A1, A2 genotype in our population to be 0.375. Lastly, let's look at the frequency predicted for the genotype A2, A2. So from our equation, we know that that genotype is represented by the term Q square, and that's Q times Q. So we know that Q is 0.25. We multiply 0.25 times 0.25. So that's Q. And that now gives us a value of 0.0625. So about 6% of our population at equilibrium should carry the genotype A2, A2. So these are the genotype frequencies we would expect to hold constant from one generation to the next. So the Hardy-Weinberg principle really is oftentimes called the null model of evolution because it's assuming that the population is not evolving. It's not undergoing any pressure that we might see coming from migration or mutation or from natural selection. So there is no strong evolutionary force disturbing that population. And that has a lot of great power with respect to species management. So if we think about perhaps a population of elephants, for example, right? African elephants, a species we're quite familiar with. And say we're dealing with a gene that may code for tusk length. And we manage to go out and we survey different genotypes, and we find that we've got 3,000 individuals that are A1, A1, and we've got 1,000 individuals that are A1, A2, A2, and we find that we have no heterozygotes in that population. So we can use our calculations to estimate allele frequencies. So allele 1 here, and you can go back and test yourself here, should have the frequency of 0.75, and our A2 allele now should have a frequency of 0.25. And again, 7.5 and 2.5 add up to 1, so we're in pretty good shape. So if we calculate, based on those values, what we expect this population to be in equilibrium, we find that for our 3 potential genotypes, for A1, A1, we would expect 56 of the population to have that genotype. We would expect about 6% to be A2, A2, and we would expect for our heterozygote here, A1, A2, we would expect 38% of the population to be carrying that. Now think about those values. At equilibrium, we have those 3 genotypes being represented. But we know from our survey that there were no heterozygotes in the population. So there is clearly a difference between what we'd expect at equilibrium, we'd expect when there's no sort of evolutionary pressure acting on this population, relative to what we actually observe. So that indicates that there's some sort of disturbance, something affecting that population. They're very different than what we would actually expect. Now there are ways to statistically examine whether the difference between what we observe versus what we expect is due to chance or whether in fact there is a statistical difference between them. And to do that, we use a test called a chi-square test of independence. And this might be one that you recall from an early stats course. In a moment, I'm going to pass you over to Terry, and she's going to build a nice spreadsheet that will sort of explain how to calculate, again, the mechanics of genotype and allele frequencies. And she'll discuss and cover various points of Hardy-Weinberg and Hardy-Weinberg equilibrium. She'll also demonstrate how to use one of these chi-square tests in order to examine differences between what we observe and what we expect. So with that said, Terry, on to you.